and welcome back to my YouTube channel. We are going to continue with this series of lectures in which we are solving all the unsolved questions and in some cases solved questions from RK Bali chapters. Knowing the importance and the frequency with which they are asked in exam, it is very crucial that we solve each and every question with proper understanding and theoretical explanation. Now, when we consider the questions from this particular chapter of measurements of DR elements, atmospheric pressure, there are a type of questions which are based on altimetry, pressure altitude, density altitude, etc. Now there are two types of questions that I can think of when considering this. First, the altimetry questions from Oxford Meteorology, which are numerical based questions, a lot of numerical based questions. I have solved that whole chapter from Oxford altimetry chapter and created a separate playlist, the link of which I will put in the description box. So when you do this chapter, also make sure that you do that chapter or the questions from that chapter. And I have made detailed videos on all the questions from that chapter. The questions can also be asked numerical based. So now let's start with a proper understanding of what density altitude is, how it affects the aircraft performance, how it is to be calculated from pressure altitude. After understanding that, we will switch to or we will directly jump to the questions related to it. So, what is a density altitude? Density altitude. Now when we fly or when we do altimetry chapter, we have come across many different types of altitude. Pressure altitude, flight level, true altitude, okay, indicated altitude, height, elevation, but we haven't heard about density altitude before or previously when solving questions. So now this concept of density altitude is one unique concept. Now considering the altitudes like true, indicated, pressure altitude, flight level, height, elevation, to gather this information or for your altimeter to show this indication in your altimeter, you put an altimeter pressure setting in the altimeter pressure setting window. So all altimeters have this facility that is called Coulson window or altimeter pressure setting window. And in that we put the current atmospheric pressure setting given by the ATC controller. When we are at the airport, we are often given QNH values. Okay, at some airports there is a tradition of following QFE. Below transition altitude, we always fly on QNH. When we cross and fly above transition altitude, we switch over to standard pressure setting of 1013. Conversely, when descending below transition level, we switch from 1013 standard pressure setting to QNH pressure setting, which is a local atmospheric pressure. In simple words, to sum up, all these kind of altitudes are based on atmospheric pressure. Okay, the vertical distances given by the altimeter will be based on the pressure that is input, okay, or that is put in the window. From that pressure datum, all your corresponding vertical distances are given to you. When we talk about density altitude, this particular altitude is based on atmospheric density surrounding you. Okay, density altitude is that altitude which is based on atmospheric density surrounding. In other words, it talks about ambient air density. It talks about ambient air density or current air density. So to obtain this density altitude, you don't have to put any kind of pressure setting in your altimeter setting window or any other procedure to be followed. This density altitude is calculated not during the flight or not when you sit in the flight, but much before your actual flight begins. So the concept of density altitude starts well before you go inside your plane. Okay, so when you go to your flight school, let's say for your cross country planning, or if you are an airline pilot, when you enter airport and you go to your office in the airport. So there is a procedure, whether you are a student pilot or a proper airline pilot or any other kind of pilot, you always sit and and file your flight plan and you do your flight planning, a detailed flight planning in which you plan your flight, whether it is a cross country from point A to point B, or it is a route or a sector that you are flying from point A to point B. If you are in an airline, right? And for that route, you make a proper plan, the net reports, the weather that you are going to expect, the weather at your departure airport, the weather at your destination airport. Okay. In consideration of all this, calculation of density altitude, knowing what your density altitude is at departure airport and your destination airport. Okay. The density altitude which you expect when you reach your destination airport. So these two calculations are very important aspect of your flight planning. Now, let's say currently, let's take one condition. You are at a particular airport, okay, and this is your plane over here. The current atmospheric pressure surrounding the airport are ISA conditions, are ISA conditions. Okay, so the atmospheric layer of air which is surrounding your airport or your aeroplane is an ISA atmosphere, or the atmosphere which has all the values of pressure, temperature, density, temperature lapse rate, pressure lapse rate, which your ISA specifies. Okay, so in this kind of atmospheric layer, the density of air at mean sea level will be 1.225 kilogram per meter cube. That is your density of air. What is the formula for density? Density equals to mass upon volume. Okay, so let's take, this is your volume. This is the volume of your of a particular air mass, and the density in it, density of the air particles, density of the air particles in it. The meaning of density is how closely packed is the object, any object, how closely packed it is, or if it is not closely packed, that means the space among its many molecules is very large. Okay, so if we say that the density of this town, of this city is very high, or density of population, that means in a very small crowd, in a very small area, there are a lot of people living in it. That means the place is crowded. If the density of population in a particular city is small, that means in a particular area, the people living there are very few in number. So density is how crowded something is or how less crowded it is. Same thing when you apply this to air mass density. Okay, density is how closely packed the air molecules are in a given particular air mass. Okay, so mass upon volume, that is means in a given volume of air mass or in a given space, how the molecules are associated with each other. Are they very far away from one another, or are they very close, or are they very close together? So when the air molecules are very close together like this, in this example, let's say, we say the density of air is very high. Opposite to this, if we take another volume of air, if the air molecules in it are far away from each other or are separated by very large distance, we say that the density in such a case is less compared to this particular example. So the density in the second example is less than the first example. Okay. Now when density of air is very high or is just high, we call that particular kind of air thick. So such a air will be thick. This air, when density of it is less, it will be called thin. It will be called thin air. Okay, thin air, thick air. Now, when density of air is very good or is very high, the performance given by your aircraft engine will be good. So this is good for high density air is good for aircraft performance. Okay. A less density air is bad for aircraft performance. Is bad for aircraft performance. That's it. Okay. Now over here we have taken a one particular aircraft at airport where ISA conditions exist. Now if we take some same aircraft, okay, I'll take a new slide. The same aircraft, a different airport. Okay. So over here we have ISA conditions. In this example, let's take conditions are warmer than ISA. In this example, let's take conditions colder than ISA. Okay. ISA warmer than ISA. And over here we have conditions which are colder than ISA. In conditions which are ISA conditions, we have density of air to be 1.225 kilogram per meter cube. Correct? We have temperature of 15 degrees Celsius. We have atmospheric pressure of 1013 millibars at mean sea level. These are the three basic conditions. And then we have dry air. Temperature of 15, pressure of 1013, and nature of air is dry. Okay. Now let's go to the second column of air, which is warmer than ISA conditions. That means over here the temperature at mean sea level is not 15 but a value more than 15. Let's say the temperature here is 30 degrees Celsius. Okay. Pressure here is not ISA pressure but a lower atmospheric pressure. So let's take 1000 millibars. And the nature of air is humid air. Now these three conditions of warm temperatures or warmer than ISA temperatures, lower than atmospheric pressure, lower atmospheric pressure compared to ISA atmospheric pressure, and humid air with humidity in it. Okay, so these three conditions are very bad for your aircraft performance. So when these three conditions combine, the total overall consequence that it will create will be a very high density altitude. What does that mean? A very high, a very high density altitude. Very high density altitude. So let's say for your example, the we are currently in this example, aircraft is currently at mean sea level, where the pressure is 1013, temperature 15, etc. Over here, in this condition, when the altitude is very high, meaning the density of air is less. Density of air is less than expected. So let's say due to warmer temperature conditions, that is temperature of 30 degrees Celsius, less atmospheric pressure and humid air, the density over here at this particular mean sea level is half of 1.225 kilogram per meter cube. So that means the density existing here is half of the density existing at ISA mean sea level. Now when density is less, okay, at mean sea level, that means your aircraft performance will be very low because the density of air where aircraft will roll down the runway for takeoff will entering the engine will be very less. Okay, over here the density of air is 1.225 kilogram per meter cube. So the air density that is entering the engine will be very high. Compared to this, over here the density of air entering your engine is very low. Thin air is entering your engine. As a result, the performance given by your aircraft engine will be very bad or will be very poor. Okay, so although you are flying from mean sea level airport, okay, you know that your elevation of airport is mean sea level, correct? But what will aircraft think? The aircraft thinks that it is operating at an altitude which is higher than mean sea level. because such kind of density of half 1.225, this density of half of 1.225, which is 50% of ISA density, will exist at altitude above mean sea level ISA. So technically speaking, you are at mean sea level. As a human being, you know that. But the power generated by your aircraft engine or the performance. Now this performance includes, what does this performance includes? Aircraft performance means the takeoff distance that will be required by your aeroplane to take off from the airport, right? So if there is a 5,000 feet runway on a very good day like IC conditions atmosphere, you will require only, let's say, out of 5,000, 2,000 feet of runway to roll down and lift off in a very on a very bad day. Bad day means, this example, when the density altitude is very high or the atmospheric air density is very very low. On such a day, you may require not 2,000 feet of runway but more than 2,000 feet of runway. Let's say 3,500 feet. Okay, so the length of runway that now you require to gain a to gain a suitable airspeed and lift off from the runway has increased. Why is that? Because of high density altitude and thin air, the air mass entering your engine is inadequate. Okay, and to make sure that proper amount of air mass enters your engine before you lift off, you will have to roll down an extra amount of runway. Okay, roll down extra amount of runway so that additional air enters your engine, which will compensate for the less air density, which is a consequence of high density altitude. Okay, so takeoff distance is the first criterion when we talk about aircraft performance. Second is the rate of climb that is given by your aircraft. Okay, after you lift off on a very high density altitude day, due to less air density surrounding you, the aircraft will climb at a very slow speed. What is rate of climb? Is how fast you climb. That means in a given amount of time you are climbing at a very fast rate. So slow rate of climb means the rate at which you are climbing. Okay, in a given particular time you are climbing very very slow, so that you will get a slow rate of climb on a bad day. That means high density altitude day. So your landing distance. Now when you enter your destination airspace and now you're going to land at your destination airport. Now if your destination airport is also a very high density altitude airport, okay, so when you land, you will not come down to a full stop very anytime soon, because let's say at your destination airport the amount of runway available to you is 5,000 feet. On a good density altitude day like ISA conditions day, let's say you require out of 5,000 only 2,000 feet of runway to come to a full stop on the runway. But in case of high density altitude day, okay, very hot day, very humid day, very low pressure atmospheric condition around you or at the airport, in such a case your aircraft will not stop at the first 2,000 feet of the runway. Let's say it will stop at 3,500 feet. So it will roll down after landing, after touchdown on the runway, it will land an extra 1,500 feet to come to a stop, because on a very high density altitude day, due to very very thin amount of air in the atmosphere, your true airspeed will be much much more than your indicated airspeed. Okay, since you are flying at a very higher true airspeed, you are coming down at the destination airport at high speed, high momentum, and therefore it takes an extra amount of runway when you touch down to dissipate that extra amount of true airspeed that your aeroplane has. That's why your landing distance increases, your takeoff distance increases, and the rate of climb given by your aircraft is also poor. So these are the bad consequences or drawbacks of a very high density altitude day. So coming back to this, your aircraft is at mean sea level, your airport is at mean sea level, and your aircraft is parked there. Okay, but when you enter your office and you start doing your calculations, you look at the Met reports, and the Met reports state that the temperatures are higher than ISA temperatures. So a hotter temperature is will create will give you a very low density of air. Okay, hotter temperatures means density of air will decrease. Okay, so your aircraft performance will be according to that density. Just because you are at mean sea level doesn't mean or is not sufficient condition to get or to promise you a very good performance or adequate performance. Along with that elevation of airport, it's at mean sea level, fine. Check the temperature of that day. Okay, temperature hotter than ISA means it's no use or it's useless being at mean sea level. Okay, so although you are at mean sea level, but the temperatures existing at your airport are not favorable for you. So aircraft thinks is at some other altitude. Aircraft thinks it is at some other altitude. In this particular case, it will think that it is a altitude or it is at an altitude higher than higher than mean sea level. It can be 1000 feet, 2000 feet, 3000 feet, anything like that. Now, how to determine that? You are at the aircraft is from outside aircraft is parked at mean sea level or is situated at mean sea level on the runway, but the performance will be equivalent to the performance that you will get when you go to some other altitude. Okay, so although you are at mean sea level, but the performance given by your aircraft will be somewhat equal to or will be like as if your aircraft is situated at some other altitude. Okay, now let's say over here half of ISA density, half of 1.225. So where you are located here, there the density is half of ISA density. Now I will show you one table. Okay, so here. For example, this time, fuel and distance to climb table. Okay, before we do that, this table. Now look, over here at 0 feet, that is mean sea level, you have a pressure of 1013.25. Now half of 1013.25 is how much? Is approximately 500. Okay, so which exists at 18,000 feet. Similarly for density, we have proper 100% density, maximum density at mean sea level. Now 50% of that density, which we have taken in our example, exists at what level? At around, let's say 56% at around same 18,000 feet or more than that. So 56 and 36. Let's take 20,000 feet. So 56% of air density exists at 18,290 feet. So 50 will, let's say, exist at 20,000 feet higher than 18,000. So let's come back to this example. So I will write here 20,000 feet. So now although, look at this example, okay, you are at mean sea level, but aircraft will generate performance or give performance or start behaving as if it is located at 20,000 feet. So there is no use of being at mean sea level or your airport being at mean sea level. The performance given by that aircraft will be as if it were at 20,000 feet. So that is a disadvantage because when you go to 20,000 feet, you will have very less density air, okay, very thin air. And the drawback of thin air is that the fuel air mixture which enters your piston engine or your this turbine engine, it will get enriched. That means more fuel, the amount of fuel that enters the engine will remain the fixed, but the amount of air that should enter the engine will be very less and will become less and less and less as you keep on climbing up in altitude. Okay, so less and less air, that means the fuel air mixture will not burn properly or efficiently. A lot of fuel will get wasted, and due to inefficient burning of fuel air mixture, the amount of power given out by your engine will also get affected. That's why the engine power decreases. Apart from engine power, you can see the takeoff distance increases, landing distance increases, rate of climb increases. So this is the whole concept of density altitude. It depends on density. It doesn't depend on atmospheric pressure like other altitudes based on QNH, QFE, standard pressure setting. Okay. So what is density altitude? It is the altitude which is expressed in terms of density, okay, which exists at a particular level in ISA. So whatever current density is existing at the airport or the ambient density existing at the airport, that density we should find in the ISA table. We should go to the ISA table and we should find over here where that particular density exists. And the level or the vertical distance corresponding to that density is our density altitude. Okay, so density altitude is the density which exists at ISA level, okay, particular ISA level. So this calculation you always have to do when you start your flight planning, okay, for your departure airport and for your landing airport, okay, because the airport you are departing from, you have to make sure that you have uh, safe amount of runway available to you for your takeoff roll, and also in the event something bad happens, you should be able to stop your plane. Even for the landing airport, where you go to land, that there should be a sufficient amount of runway length available to you to come to a full stop, okay, safely. So for this reasons, you have to calculate density altitude. Also for your rate of flight at departure airport as well as landing airport, because in the event of missed approach or go around, you have to climb. So you should get proper rate of climb. You also should get a proper climb gradient so that you cross or you pass all obstacles with safe margin. So that is why this concept is very important of density altitude. Now in colder than ISA conditions. Now in third example, you have temperatures, let's say, which are colder than ISA. So let's say it's 10 degrees Celsius. Pressure is higher than atmospheric pressure, let's say 1030 pressure, and air. The nature of air is not fully dry but not very humid. So I will write here less humid air, less humid. Okay. Now these conditions are very favorable for your aircraft performance, because colder the air gets, the more the density of air will increase. Okay. So I'll write here colder air means your density increases. Density will increase. Same as pressure goes on increasing as you come down altitude. Okay. As you climb down, you descend. Okay, your altitude decreases. With decrease in altitude, your atmospheric pressure increases, right? So as pressure increases, your density also increases, because now the weight of column of air that is upon an object will weigh heavily or more heavily, and less humid air means the mass of air is more, and as a result its density will also increase. So all these three elements, they will combine to give a low. Compared to this, the density altitude here will be low, low density altitude. Okay, so low density altitude means density of air is more than ISA. In this particular example, all three conditions have okay have outdone the ISA conditions. Temperatures are colder than ISA. Pressure is at mean sea level is also below is also higher than ISA pressure. Air not completely dry but less humid. Okay, so almost dry. So density of air we can say it's more than ISA. That means the performance given by your aircraft will be better than the performance that we experience here. that we'll witness here. Okay, so better rate of climb, much better rate of climb, a shorter takeoff distance. So in on this day, if you require 2000 feet, over here where density altitude is low, density of air is very high, that means the air is thick. Okay, so much more amount of air will be entering the engine. Efficiency of your aircraft engine will increase. The lift, the generating capacity will augment. Okay, so everything will be above our expectations. Okay, and as a result, if here you need 2000 feet,